Hello students, congratulations for staying with us all the way to the end of the H2 curriculum. So we have come to the last topic, which is on introduction to the chemistry of transition elements. You might have heard from your seniors that this is a relatively dry topic which requires a lot of memory work. Nothing is further from the truth. In fact, this is arguably the most interesting topic out of most of the chemistry topics which you have learned. The reason why you might not have felt so is because of the fact that our H2 curriculum is written in such a way that it is a little bit biased towards organic chemistry. You learned a lot about functional group interconversion, the various organic functional groups, the tests, etc. But do take note that you might have remembered from your various qualitative analysis laboratory experience that you observe a lot of colors, and these colors are due to transition metals complexes. Okay, yep. So if you wish to learn more about them, you might want to read up more on your own from the various resources we provided for you, or you can go to the library to borrow the necessary text. Yep. If not, then I will just go through with you the gist of what you need to know for H2 curriculum, and if you just follow us through the lectures, you will be able to understand at least at a very shallow and very on the surface level what exactly is transition elements. Okay, yeah, so we will dive straight into the learning objective. So for the learning objective, you notice that it's written that for the first sets of transition elements, the focus is from titanium to copper. Okay, then you were told that you need to explain what is meant by transition elements in terms of D block elements forming one or more stable ions with partially filled D subshells. Yeah, so I hope from the definition you are aware that if the metal or if the D block elements wants to qualify as a transition elements, it needs to form at least one or more stable ions with partially filled D subshells. And from the periodic table, you know that for the first row transition elements from scandium all the way to zinc, you might notice, or if you recall from what you have learned from atomic structure, that the electronic configuration for scandium is the argon configuration, and then followed by 3d14s2. And usually scandium behave very much like a main group elements because the stable cation it forms is scandium 3+. So if it's scandium 3+, that will make its electronic configuration that's of argon, yeah, which does not have a partially filled 3D subshells. Yeah, so in that case, scandium does not qualify to be a transition element by definition. Yeah, by this particular definition, when you are being told that transition elements forms one or more stable ions with partially filled D subshells. Okay, using the same logic, zinc will not satisfy the criteria as a transition element as well. The reason being, zinc has the electronic configuration, argon configuration, as well as followed by 3d10-4s2. So the zinc chemistry which you are aware of is usually zinc 2. Yep, if you look at zinc 2, its electronic configuration is argon configuration followed by 3d10. So that will mean that it has a filled 3D subshells. So again, it doesn't qualify zinc to be a transition element. Yeah, so that is why based on this particular definition from your learning outcome, only titanium all the way to copper, these 8 elements qualify to be transition elements. And out of the 8 elements, you are only required to be quite familiar, okay, or you just need to have a little bit of familiarity with chromium, manganese, iron, and copper. The rest, they are found in your data booklets, but you do not need to be extremely familiar with them. Yeah, so we have created several videos on vanadium chemistry. Some of you might have done vanadium chemistry in the lab. Vanadium chemistry is very interesting. Yeah, so if you want to look at the chemistry of vanadium, you can click on the link below, which contains video to the different colors of vanadium. Okay, some of you might also have chanced upon the earlier video I did on cobalt. Yeah, so there are many beautiful chemistry on cobalt. So if you are interested, you can also click on the link below where we'll discuss chemistry of cobalt. Okay, the rest of the elements, you would have seen them once in a while, especially when you were in secondary school. Okay, so without further ado, we'll just jump straight into discussing the other learning objective. For 13b, state the electronic configuration of a first row transition element and its ions. Again, you have learned them in atomic structure and physical periodicity. That's the topic number 1. So we are quite confident that you will be able to write down electronic configuration of first row transition elements. Okay, then if I just jump back to the periodic table and I'm just going to erase these, you will notice that, or if you can recall, chromium and copper are the special case in terms of electronic configuration. Yeah, so if you recall, for calcium, it will be argon configuration followed by 4s2, and then scandium will be 3d1 4s2, titanium 3d2 4s2, vanadium 3d3 3d3 4s2. Yep. Then for chromium, it is not 3d4 4s2, it is actually 3d5, 3 is argon followed by 3d5 4s1. Yeah, the reason, as what you have heard or what you have recalled from the learning of atomic structure, is that half-filled orbitals tends to allow the system to have greater stability. Yeah, that also has got to do with pairing energy. Yeah, because of the fact that when I have more orbitals or subshells that are half-filled, yeah, that actually stabilize the system. And then as I move on to manganese, iron, cobalt, nickel, copper, so copper is expected to have the electronic configuration 3d9 4s2, but instead it has the configuration of argon 3d10 4s1. Yeah, so it has a filled 3d subshells followed by 4s1, which is half filled. Yeah, so this is desirable. Okay, yeah, so do know the exceptions, and if you are interested in the second and third row transition elements, you do not need to worry too much about them, because even in undergraduate courses, they do not talk too much about them, because they tend to have special or some reactivity which are quite different from the first row transition elements, and especially the third row. This is largely due to the fact that prior to the third row, right, you are filling up the f orbitals, okay, or the f subshells, and the third row transition elements tends to have relativistic effects, or relativistic effect tends to be prominent, and that explains the many unique appearance and chemistry of the third row transition elements. So for example, mercury is a liquid. Okay, so out of all the elements, mercury is one of the two liquids, or one of the two elements which are liquid at room temperature, the other one being bromine. Yeah, and the reason why mercury exists as a liquid is due to the relativistic effect, because its core, its electronic core, tends to be more of a noble gas, tends to take on more of a noble gas-like structure. And then if you look at gold, gold would not be gold in color if not for the relativistic effect. Yeah, so if you are interested, you can read more about relativistic effects. And these groups, they tend to be very good catalysts. So over here, yeah, okay, so we call them the platinum group elements. So they tend to show very promising catalytic behavior. So you will notice that many catalysts, they tend to be rhodium, palladium, ruthenium based, if not, and iridium based as well. Yeah, so but of course we will not discuss too much chemistry about them, because they are largely definitely not within the H2 curriculum framework, and you need to understand a lot more before we can do any meaningful discussion about them. Okay, yeah, then for 13c, explain why atomic radii first, i.e. of transition elements, are relatively invariant. Okay, so again, you can look at the explanation within the topic of atomic structure and physical periodicity. Okay, and then 13d, contrast qualitatively melting points, densities of transition elements with those of the S block. So they tend to have way higher melting point densities. So you need to understand why. And transition elements tends to have variable oxidation states. Okay, and then of course predicts from given electronic configuration the likely oxidation state of the transition element. This is not easy, honestly, it's not easy. Yeah, so in most cases oxidation states needs to be known or studied beforehand, okay, before you can apply them confidently. Yeah, of course not all. There are cases which will ask you to predict, but that tends to be quite simple cases. Okay, learning objective 13G is something which it's really common because you have encountered them in electrochem. Yeah, so it's supposed to describe and explain the use of iron 3, iron 2, permanganate iron 2, and dichromate chromium 3. Example, redox systems. So you're asked to refer to electrochem. Okay, then of course another learning objective on electrochem, predict using E0 values, likelihood of redox reactions. Okay, 13I onwards will be more interesting. Okay, you need to know what ligand means and what complex means, as exemplified by copper 2 ions with water. Yeah, so that will be the hexyl aqua copper 2 complex. Ammonia, that will be the tetraamine copper 2 complex, as well as chloride, that will be the tetrachloro copper 2 complex as well. Okay, as ligands. So yeah, include transition elements, transition metal elements, metal complex found in the QA notes. Okay, so that means that when you study transition elements, you also cannot run away from understanding a lot of these colors. Okay, so you notice whatever given here is whatever's likely to be in your syllabus. So that includes chromium, copper, iron 2, iron 3, manganese 2, and these are the few. Okay, zinc, we included it, although it's not, strictly speaking, it's not a transition element. Okay, yep. And then explain qualitatively that ligand exchange may occur, as exemplified by the formation of the complex, including color changes involved. Okay, color changes. So for example, when ammonia ligand displaces water ligand in the copper complex, the color turns from pale blue to dark blue. Okay, and as well as carbon monoxide oxygen exchange in hemoglobin. So this is another learning objective which you need to be familiar with. Okay, then 13K, describe using the shape and orientation of d orbitals the splitting of the degenerate d orbitals into two energy levels in octahedral complex. Okay, so notes the focus in H2 curriculum only octahedral complex. So strictly speaking, for octahedral complex, I have a metal in the middle, and then I have 6 ligands, and strictly speaking, all the ligands must belong to the same type of ligands. Okay, if they are different types, strictly speaking, it is not called an octahedral complex. Okay, but of course you can use that as a proxy. 13L, explain in terms of d orbital splitting and dd transition why transition element complexes are usually colored. Okay, do take note of the parts which is not in your syllabus. Knowledge of the relative order of ligand strength is not required, although sometimes in a data response question we might give you the strength of ligand and then ask you to predict based on the color observed, what do you think is the strength of the ligand. Okay, and then for 13M, explain how some transition elements and or their compound can act as catalysts. Yeah, so we have covered this briefly under reaction kinetics. Okay, so these are the references which you might want to read if you think that you want to understand more on transition elements. I really suggest you guys to read more if you are interested, especially on inorganic chemistry, because for organic chemistry you guys are very familiar. There's a common language, and you tend to see many molecules transforming from one to the other. Inorganic chemistry you are not very familiar with, so whenever a question is provided for you, given to you, asking you to deduce and observe the data and then find some trends, it might be a little bit more challenging if you are not used to looking at transition metal complexes. Yeah, but that is not to say that if you don't look at them, you will be disadvantaged. No, you will still be okay, except that you will need a little bit more time lah. But I mean, most of you, given enough time, you should be able to get the correct answer. Okay, yeah. So we'll jump straight into the definition. So I think we have briefly discussed the definition. Transition elements are d block elements, forms one or more stable ions in partially filled subshells. Yeah, the subshell need not be 3D. For first row transition elements is 3D. For second row is 4D. Third row will be 5D. Okay, so you do not need to qualify it. Yeah, so by definition, scandium and zinc are excluded. We have explained that. Okay, so these two cases we have already explained. And then the electronic configuration of the first row transition element, which has been covered in topic 1, are listed over here. Yeah, so you probably do not need me to go into details in how do I arrange the electrons and represent it using the electron inbox representation. Yeah, but do take note that the exception is chromium, which you need to be aware of, as well as copper. Okay, so instead of 3D4 4s2, it's 3D5 4s1. Instead of 3D9 4s2, it's 3D10 4s1. Okay, but please do not assume that if copper is like that, then the element below copper is also like that. Yeah, so you'll be surprised. The elements right below copper is silver. Silver is actually not 4D10 for 5s1. It's actually 4D9 5s2. Yeah, so again, when the subshell, when the principal quantum shell becomes bigger, yeah, there are a lot of new rules coming into play, or there are more exceptions than norms. Yeah, so in fact, transition elements, if you study in university, you will be told that there are more exceptions than norms. And of course, if you notice, in the most simplistic level, there is something known as the 18 electron rule, because for transition elements, the maximum number of electrons that you can put in the outermost shell is 18. Why is it 18? Because you have 3s, okay, which can fill 2 electrons. You have 3p, which can fill 6 electrons in total, and then you have 3d, which can fill 10 electrons in total. Yeah, so you might have heard from your seniors, or even read about it. Read about it in textbooks, or even online sources, something called the 18 electron rule. Yeah, so do not come as a surprise if you have seen that. Okay, and then these are the cations form. Usually what is shown here is the common oxidation state. Of course, iron 3 is not shown, manganese 3 is not shown. All this, yeah, doesn't really matter. So we just show you the most common and probably the most stable ones lah. Okay, so I don't need to go into details as well. Okay, 1.3, physical properties of transition elements. So this actually covers 2 learning objectives, 13C and 13D. Okay, so atomic radii and ionization energies of the transition elements are relatively invariant. Okay, so please refer to atomic structure if you cannot remember how to explain why. Okay, and then of course the melting point are higher than S block. Okay, because both the 3D and 4s electrons are involved in metallic bonding, so they are parts of the sea of delocalized electrons. So that means that the metallic bonding within the transition elements or the transition metals are likely to be stronger and more extensive. Okay, the density of transition elements are also higher than S block, because the atomic radii of transition elements are smaller than the S block elements. Okay, how can we understand that? We can just take a look at some of the data we have. Okay, so for example, for transition elements, over here, because over here we mentioned that atomic radii are smaller than S block, right? So if we simply just compare atomic radii, so for the D block elements, it's between 0.125 to 0.146 thereabouts. Okay, for group 2, okay, you notice that calcium and above is 0.197 and above. Okay, so that explains why there is a huge difference in terms of the size. Yeah, because as you go across the periods, electrons are being added to the same principal quantum shell. Okay, and then the nuclear charge increases across the periods. Yeah, so in that case, the effective nuclear charge increases across the period, and the outermost electrons are attracted more strongly towards the nucleus. Okay, then we have a exercise 1.1 over here, so which we can have a brief discussion. So for exercise 1.1, we were told that calcium is a fairly soft silver gray metal which quickly tarnish in air, so it does tells you that it is highly reducing, which tends to react with oxygen, and in the process probably produces calcium oxide or calcium hydroxide. Okay, likely to be calcium oxide first. Vanadium is a hard gray metal which is resistant to corrosion at ordinary temperature. So metallic calcium has no commercial uses. Vanadium is widely used as an alloy element in steels. So data about calcium and vanadium are given below. So you are given electronic configuration, you are given the atomic radius, okay, you are given a melting point. You can see that vanadium is twice as high. You are given the density. You notice that the density is about 4 times greater than that of calcium. So question is, the melting point of vanadium is significantly higher than that of calcium. Explain this in terms of the types and strength of bonding in each metal. Okay, so as I mentioned earlier on, in the generic examples given here, so here I can be a little bit more specific. Okay, so both of these metals within the metallic structure, they have metallic bonding. Okay, so metallic bonding will be one of the key idea you need to impress upon the examiner. So you have metallic bonding. Yeah. However, for calcium, right, it's only able to contribute 2 electrons to the C or D localized electrons. Okay, so on the other hand, for vanadium, it is possible to contribute up to 5 electrons into the C or D localized electrons. Yeah. So because of that, I mean, after contributing 5 electrons to the C or D localized electrons, vanadium will exist in a higher oxidation state as compared to that of calcium. Yeah, so with that, it will have a smaller cationic radii as compared to Ca2+, okay, and then a smaller cationic radius with a greater charge. So that means that the charge density of vanadium is greater than that of calcium. Yeah. Then at the same time, I expect the metallic bonding, which involve the electrostatic force attractions between the C or D localized electrons and the positively charged cations, yeah, is likely to be stronger and more extensive for vanadium as compared to that in calcium. Yeah. So because of that, more energy is required to overcome the metallic bonding within vanadium as compared to that within calcium. So that leads to a higher melting point. Okay, so what are the main contributing factor? The number of electrons contributed into the COD localized electrons per atom, as well as the charge and radius of the metal cation which results. Okay, then for part B, explain why the density of vanadium is significantly higher than that of calcium. Okay, I think first of all, we need to recognize that for vanadium, the atomic radius is smaller than that of calcium. Okay, so that's number one. Atomic radius is smaller. Okay, what about AR? So the AR is not mentioned here. Okay, so if you can simply just refer to the periodic table if you wish to look at the relative atomic mass, but of course you do not need to. Yeah. So for the relative atomic mass of calcium is 40.1, vanadium is 50.9. Okay, 40.1, then this is 50.9. Okay, 50.9. Okay, yeah. So because of that, I am able to pack more vanadium, okay, into a unit volume of the solid lattice. Okay, and if I can pack more vanadium, so that means that I will have more atoms and heavier atoms per unit volume of the solid lattice. So this actually gives rise to a greater density. Okay, yeah. Why is it that I can pack more vanadium into a unit volume? The reason is because the vanadium atomic radius is significantly smaller than that of calcium. Yeah, so therefore per unit volume I can pack more vanadium, and at the same time the mass of the vanadium atom is greater than that of calcium. Yeah, so the mass per unit volume of vanadium is likely to be greater than that of calcium, and that explains why the density of vanadium is greater than that of calcium. Okay, yeah. So we have attempted A and B. Next, we'll move on to the chemical properties of transition elements. The following are the 4 properties transition elements differ from their S-block counterparts. The first one is transition elements have variable oxidation states. Okay, so this is not surprising. For example, in JC1, when you were doing permanganate iron 2 titration, yeah, you'll notice that permanganate gets reduced from a +7 oxidation state to a +2 oxidation state of Mn2+. And then if there isn't sufficient acid being added, you might end up with manganese dioxide, which takes on a +4 oxidation state. And iron gets oxidized from iron 2 to iron 3. Yeah, and of course, to begin with, iron begins with a 0 oxidation state. So if you subject solid iron to some acids, it will first be oxidized to iron 2, and then in the presence of air and oxygen, iron 2 will be oxidized to iron 3. So the solution will slowly turns from pale green to yellow. Okay, you are also familiar with the catalytic property of transition elements. Okay, so what are the catalytic property we are talking about? So for example, in secondary school, you learn about the Haber process, that is in the manufacturing of ammonia. You learn that iron can be used as a catalyst in the Haber process. Okay, you also learned about catalytic hydrogenation of alkene when nickel is used. Okay, so beyond nickel, you know that you can also use platinum, you know that you can also use palladium. Okay, but they are not the first row transition elements, so usually we will give them a miss in our studies. Okay, yeah, you also learned about vanadium 5 oxides in the contact process. Some of you might have learned this. It's usually one of the application examples teachers in secondary school will use besides talking about ammonia. Okay, so this contact process is being used to manufacture sulfuric acids. Vanadium 5 oxide exists as a solid as well. Okay, what about homogeneous catalysis? So iron 2 aqueous ions can be used as a homogeneous catalyst. Yeah, because in the presence of peroxy disulfates, yeah, it's being a very strong oxidizing agent. Technically, peroxy disulfates is able to oxidize iodides directly into iodines. Okay, so this is possible into iodine plus S4O8. Oh, sorry, SO4 2 minus 2 of it. Yeah, technically this is possible. Yeah, but this is only based on thermodynamics sentiments. Kinetically, the reaction will take on a relatively large activation barrier because both species are negatively charged. Yeah, so iron 2 comes to the rescue. Yeah, because iron 2 can easily react with peroxy disulfates, and in the process, peroxy disulfate will be reduced to sulfates, and iron 2 will be oxidized to iron 3. Yeah, and iron 3, as what you might have remembered from your laboratory work, iron 3 and I minus will react to produce iron 2 and iodine. Yeah, so indirectly, when iron 2 shuttles between the two oxidation state +2 and +3, it helps to oxidize iodide to iodine and at the same time reduces peroxy disulfate to sulfate. In the process, iodide and peroxy disulfate, they do not need to meet each other, so they are not involved in reaction directly. Yeah, so what they do is they exchange electrons with the iron 2, and of course iron 2 donates the electrons and iron 3 gains the electrons from iodide. Okay, yeah. Transition metal complexes, or rather transition element, also tends to form complex ions. Yep, although you can argue that aluminium forms complex as well, because aluminium, you are able to form hexyl aqua aluminium complex. Okay, and magnesium also forms a hexyl aqua Mg2 plus complex as well. Yeah, so I'm not exactly referring to the aqua species, but I'm referring more to the species other than water. Okay, so for transition elements, many electron-rich species can act as ligands. Okay, later on you'll learn them as ligands. Yeah, so ligands, examples of ligands are ammonia, cyanide, water. Okay, yeah, so formation of complex is quite a big thing for transition elements. And one of the key misconceptions students might have regarding transition element complexes is that the complex needs to be charged. This is not true. Okay, so I will quote you a complex that is not charged. This is the tetracarbonyl nickel 0 complex. Okay, yes, I'm not wrong. Okay, the nickel has a 0 oxidation state, and the carbon monoxide ligand also is not charged, so it donates its electrons to the central nickel metal atom through the lone pairs of electrons on carbon. Okay, yeah. Then the fourth one, we are looking at formation of colored ions. Yeah, so transition elements tends to have very beautiful tends to form very beautiful complexes, and because of the various number of electrons in their d subshells, they are able to undergo, later on you'll learn them as DD transition, or for the case of permanganate and dichromate, charge transfer. Okay, but we are not going to charge transfer for the H2 curriculum. Yeah, so in general, the color ions in transition metal, there are 2 to 3 phenomena which we can explain their colors. One is known as DD transition, another one is known as charge transfer. Okay, so there are 2 types of charge transfer. One type is called metal ligand charge transfer, another type is known as ligand metal charge transfer, but they are not in your syllabus, so you do not need to worry too much about them. Yeah, you just need to worry about DD transition, which will be explained to you in due course. Okay, next we move on to section 2 on variable oxidation states. Okay, so you are aware that the 4s and 3d electrons, in terms of their electronic energy level, they are quite close to each other. Yeah, so that means that once the 4s electrons are being removed, some or all of the 3d electrons can also be removed without inputting much energy. There is of course a limit to the number of 3d electrons which can be removed. So for example, if you take a look at this particular table, we have scandium all the way to copper and zinc, of course, and you notice that from scandium all the way to manganese, the number of 3d electrons, okay, increases from 1 in scandium all the way to 5 in manganese. Yeah, so for manganese, it is already the extreme. We call that the middle point, where 2 4s electrons are being removed and 5 3d electrons are being removed. Yeah, so manganese is able to achieve the highest oxidation state possible, given by the number of 4s and 3d electrons. Yeah, however, when we move on to the next element, which is iron, you'll notice that its maximum oxidation state doesn't go to +8. Yeah, so it is like a balance. Yeah, then you can argue that, oh, I mean, since the highest oxidation state of manganese can be stabilized by oxo atoms, for example, in permanganate you have 3 MnO double bond and then one MnO single bond, right? But then you'll be thinking, then for iron, that can also be the case. No, that cannot be the case for iron in its +8 oxidation state. Yeah, so iron is not able to reach +8 because, again, as I said, it's a balanced. So if it reaches +8, it will be very, very reactive, super oxidizing, and not stable to exist. Yeah, so you'll notice that this is like a pyramid shaped. Okay, it is shaped this way. Yeah, so it's like a mirror. So like Mn is like right in the middle, and then chromium and iron tends to have a maximum oxidation state of +6. Vanadium and cobalt tends to have a maximum oxidation state of +5. Of course, not all the oxidation states are stable. Okay, so the stable oxidation states are highlighted in gray over here. There isn't a need for you to memorize them, so let me repeat. You do not need to memorize them. Any of the things you want to check out, you can always check out from the data booklet. Yeah, whatever stable oxidation state which could exist will be found in the data booklet. Okay, yeah, and then of course, in contrast, the S block elements can only form +1 oxidation state for group 1 and +2 oxidation states for group 2. Okay, you are not able to remove any electrons beyond the outermost shell, because that will require too much energy. Yeah, so remember, in atomic structure, yeah, say for a group 2 elements, its third IE is usually very high in energy because that involves removing electrons from the inner quantum shell. Okay, scandium and zinc, they are not parts of the transition elements, so you notice that they tend to form compounds with only one oxidation state, not multiple. Okay, so scandium will be +3, zinc will be +2. Okay, yep, so I think I have mentioned some of the important bullet points over here. Okay, the first one I don't think I need to talk about. The second bullet point will be the maximum oxidation states of the transition element will be all the available 3d and 4s electrons until manganese. Okay, beyond manganese, no. Yeah, so it's a balance between whether it is stable enough to exist, or whether there's enough energy inputs to remove the electrons. Okay, lower oxidation state they tend to be ionic in nature. Yeah, so for example, manganese 2 chloride, yeah, and then manganese oxide as well. Yeah, and then the higher oxidation state, that they tend to exist as what we call polyoxo anions. Yeah, so all these are called polyoxo anions. Why is it called polyoxo anions? Because they need a lot of oxygen to stabilize those very high oxidation states. Okay, and they are anions because they take on a negative charge. Yeah, so they tend to have metal oxygen covalent bonds. Yeah, you have not heard wrongly. These are metal oxygen covalent bonds. Yeah, so in fact, after you learn this topic on transition element, you'll notice that there are far more metal non-metal covalent bond than there are for ionic bonding. Okay, yeah. Then the number of available oxidation state increases from titanium to manganese. I think we talked about that. Decreases from manganese to copper. Okay, then after manganese, pairing of d electrons occurs. So there's a decrease in number of electrons available for bond formation. So I think a reason is being given here. So that explains why there's a decrease in the number of oxidation state exhibited by elements beyond manganese. Okay, so yeah, this is one of the reasons which you can cite, okay, if you wish to. Yep. Okay, so let's move on to exercise 2.1. Okay, so there are 3 questions in total. The first question reads, the table shows the possible oxidation states of the 5 D block elements in the periodic table. So the elements are represented by letters, which are not their symbols. I think it needs to be mentioned, because if not, you'll be confused. Okay, yeah, so they are given here. You are asked which of the following ions is likely to exist. Okay, so how do we go about doing this kind of question? Okay, so the easiest way to do such question is find out the oxidation state of the elements in the polyoxo anions. Okay, so for P, for option A, the oxidation state of P will be +4. For option B, the oxidation state of Q will be +7. Okay, and then oh sorry, not plus 7, plus 5, my apologies. Okay, so this will be plus 5. Okay, then for C, the oxidation state of R will be plus 6. Okay, then for T it will be plus 6. Yeah, so let us look at the list. The possible oxidation state for P is plus 3. Okay, so it doesn't quite match what we have here, so A cannot be the answer. The maximum oxidation state for Q seems to be plus 4, so this is plus 5. It doesn't match. Maximum oxidation state for R is plus 5 over here, but what was given is plus 6, so it doesn't match. Maximum oxidation state for T is plus 6. Okay, over here we have plus 6. Sorry, maximum oxidation state of T is plus 7, not plus 6, plus 7. Yeah, oh, and plus 6 is possible. Yeah, so over here, option D, we have T taking on a plus 6 oxidation states. Yeah, so therefore T is likely to exist. Okay, so not an issue. Titanium has the electronic structure 1s2, 2s2, blah blah blah, 3 and then 3d2, 4s2 as the valence shell. Which of the following compounds does not exist? Okay, so again, let us try to determine the oxidation state of titanium. So for option A, titanium will exist as a polyoxo anions, TiO4 2-. So in this case, titanium will take on an oxidation state of plus 6. Yep. And option B, the species will be TiF6 3-. So in our case here, titanium will take on an oxidation state of plus 3. Okay, TiCl3 plus 3, that's clear cut. TiO is plus 2. Okay, so having 4 valence electrons, okay, B is possible, C is possible, D is possible. So therefore A is the one that is not possible. Yeah, so I will pick A as the answer because titanium cannot reach plus 6. Why is that the case? Because reaching plus 6 will involve removing electrons from the 3p subshell. That will mean that these are being removed from the inner quantum shell. Okay, yeah. Next, we have question 3. The electronic configuration of vanadium is argon configuration 3d34s2. Which of following ions does not exist? Yeah, so again we go through the same thought process. VO2 plus is plus 4 for vanadium. This is plus 5. Okay, VO3 2-. Okay, so that will be plus 4, and then VO4 2-. Vanadium with plus 6. Yeah, so again 5 valence electrons, I can't reach plus 6. Yeah, so I should be choosing option D as my answer. Okay, yeah. Then next we have the next mini section, redox reactions involving transition elements. Okay, so this is one of the learning objective. You are supposed to describe and explain the use of iron 3, iron 2, this particular pair, permanganate, manganese 2, and dichromate, chromium 3 as examples of redox systems. I do believe that you are very experienced in this in JC1. Okay, so again, we can just briefly run through it. Yeah, so common redox system involving transition element, iron 3, iron 2, so yellow and pale green. So in this case, the iron 3 and iron 2 aqua species can potentially act as homogeneous catalyst. Yeah, in our case here, reaction between iodide and peroxo disulfate. Okay, then permanganate and manganese 2. Permanganate can be used as an oxidizing agent to oxidize primary alcohols as well as secondary alcohols as well as aldehydes. Okay, so permanganate can also be used as a reactant to effect oxidative cleavage between CC double bond, as well as to perform side chain oxidation on side chain attached to the benzene ring. Okay, dichromate, chromium 3, we are also familiar with it because it is often used to oxidize primary alcohols to aldehyde and then to carboxylic acid. Okay, and of course secondary alcohols to the ketone. Okay, then to predict whether a redox reaction is feasible or to explain color change, we can make use of E0 values of the relevant species. Okay, to find an E cell. We learned about this in topic 20 on electrochem. Okay, so there's a reason why we taught we teach transition elements after electrochem, because the two topics are intimately related. Okay, then the best way to learn this is to use an example, which is exemplified by exercise 2.2. Okay, so you are supposed to quote using relevant E0 values from data booklets, explain each of the following observations, write balance equations. Okay, the green PPT obtains when aqueous sodium hydroxide is added to iron 3 sulfate rapidly turn brown on exposed to air. Okay, so first of all, you need to learn from your QA experience. What is the green PPT? So the green PPT is iron 2 hydroxide. Okay, if it's iron 2 hydroxide, system is likely to be in the alkaline medium. Yeah, then when we pick information from the data booklets, we need to make sure that we pick the correct ones, which means we need to pick the one that is involved in the alkaline medium. Okay, because we are dealing with the reddish brown iron 3 hydroxide and the dirty green iron 2 hydroxide, this will be the equation we are picking. Okay, so with the reduction potential value of negative 0.56 volts. Okay, so I'm going to write it down first. So Fe bracket OH3 plus electrons equilibrate to give us Fe OH2. Okay, and this solids. So the E0 is negative 0.56 volts. Okay, yeah. Turn brown on exposed to air, so that means that in the presence of oxygen, again, the medium is alkaline, so we must make sure that we choose the correct equation involving oxygen being reduced to OH minus. Okay, so we're going to choose this. Okay, so therefore it will be O2 gas plus 2H2O liquids plus 4 electrons equilibrates to give us 4OH minus aqueous, and then the reduction potential value is plus 0.40 volts. Okay, so first of all, we need to check whether the reaction is feasible. So we're going to calculate E cell. So E cell, okay, is equals to E reduction minus E oxidation. Okay, so that will be E of O2 OH minus E oxidation. So FeOH3 slash FeOH2. Okay, so this is equals to plus 0.40 minus 0.56. Okay, so we're going to end up with plus 0.96 volts. Okay, so this is greater than 0 volts. Therefore, the reaction is spontaneous. Yeah, so therefore, iron 2 hydroxide will be rapidly oxidized to iron 3 hydroxide on exposed to air. Okay, so this is what we can do using standard reduction potential. And then we are supposed to write a balance equation. So we're going to multiply the iron 3 hydroxide equations by 4. Okay, so we're going to end up with 4 FeOH2 solids plus O2 gas plus 2H2O liquids. I'm going to get 4 Fe bracket OH3 solids. Okay, so feasible reaction. In part 2, we were told that the blue solution containing chromium 2 obtained by dissolving chromium metal in dilute sulfuric acid slowly turns green even in the absence of air. Okay, yeah, so this is in acidic medium, so we have to take note of the medium in our discussion. Okay, yeah, so first of all, we need to choose the correct system. Chromium, where are you? Chromium. Yep, chromium is over here. So we're going to choose chromium 3, chromium 2. Okay, so so that's part 2. Okay, we're going to choose chromium 3 aqueous plus electrons to get chromium 2 Okay, then this is 0.41 volts. In fact, it's minus 0.41 volts. Okay, we can also take a look at chromium 2 to chromium metal, although I don't think we need to take a look at this because we are looking at the oxidation of chromium 2 to chromium 3. Okay, so we can ignore this first, but I mean, if you wish to, you can, because you know that the chromium metal first oxidized to chromium 2. Okay, it's given here, dissolving chromium metal. Okay, so if you want, you can just put this in. Okay, so chromium 2 plus aqueous plus 2 electrons, chromium solids, this is minus 0.91 volts. Okay, so we are looking at an acidic medium, so definitely we are looking at the hydrogen H plus half cell, or H plus hydrogen half cell. Okay, then this is 2H plus 2 electrons. I'm going to get H2 gas. Okay, so this is 0.00 volts. Okay, so to prove that or to support the oxidation of chromium to chromium 2, we will calculate E cell. So first, chromium solids plus 2H plus aqueous to get Cr2 plus aqueous plus H2. Okay, so we'll try to calculate the E cell. So the E cell is equals to E reduction minus E oxidation. So that will be E of H plus H2 minus E of Cr2 plus Cr. Okay, so this will be 0.00 minus 0.91. This will be equals to plus 0.91 volts. Okay, so we do the same thing and check whether chromium 2 can indeed be oxidized to chromium 3. Okay, so let's check this out. We're going to end up with Cr3 plus aqueous. Okay, so I think I will need 2 of this. Okay, plus H2 gas. Okay, so in this case, E cell will be equals to E reduction minus E oxidation. Okay, this is equals to 0.00 minus 0.41 plus 0.41 volts. Okay, yep. So I hope you find the calculation straightforward. I think it's a little bit more straightforward than what you expect from electrochem. So that is why a strong background in electrochem helps a lot. And there are a lot of fuel cell which uses transition elements. Do take note of it. Yeah, so a large number involve they are vanadium based. So we will probably work on some of them during our transition element or electrochem tutorials. Okay, yeah. Next, we're going to move on to section 3 on the catalytic properties. Okay, yeah. So, well, I mean, we learned about catalysts in JC1 under the topic on kinetics. Okay, so you might want to review kinetics as well as the modes of action of catalysts in that particular set of notes. Okay, so there are 2 types of catalysis. One is heterogeneous, the other one is homogeneous. Okay, over here we are going to make use of our knowledge of reduction potential value to explain the mechanism of homogeneous catalysis. Okay, so remember the definition. A catalyst is a substance, okay, where it will provide an alternative pathway with a lower activation energy for the reaction to take place. Yeah, so remember that the catalyst does not alter the actual reaction pathway. Remember that the actual reaction pathway is intrinsic, so it is defined by the reaction system. It's like, for example, if you go from point A to say point B, you can either climb up the hill, okay, or you can drill a hole through the mountain. Okay, just drill a hole through and then you go by this way. Yeah, but does it change this pathway? No, it doesn't change. This pathway still exists. Yeah, you are just merely going through an alternative route to B. Yeah, so do remember that. Okay, yeah. So transition elements and their compounds, they can act as both homogeneous and heterogeneous catalyst. Homogeneous means the catalysts are in the same phase, okay, as the reactants. Heterogeneous means they are in different phase as the reactants. Okay, in most cases, heterogeneous transition metal catalysts are solids, are existing in the solid state, and it's usually the metal itself or one of its compounds. Usually it's oxide. Okay, then the reason why the transition metal or its compound can act as catalyst, yeah, it is due to the fact that it's able to shuttles between the variable oxidation states of the transition elements. Okay, if it can shuttles between the two oxidation states, it can then operate through two separate pathway to produce new compounds along the way. Okay, for heterogeneous catalysts, we are looking at the fact that the transition elements have available or partially filled 3D orbitals to accept the electron pairs. Okay, so this will allow say the gaseous molecules to be adsorbed onto the system, so it will just form weak interaction on the surface. Yeah, and then the weak interaction will result in the weakening of the critical covalent bonds within these covalent molecules. Yeah, and in the process increases the surface concentration, so allowing the reaction to take place at a faster rate because the activation barrier is likely to be lower due to the weakened bond. Okay, yeah, so if you need a fuller explanation, you might just want to revisit the kinetics set of lecture notes, or you can review the kinetics lecture last year. I think it should be topic 6 under reaction kinetics. Okay, yeah. Then we're looking at heterogeneous catalysts. We have seen this example in a Haber process. So in our case here, hydrogen and ammonia gets adsorbed onto the surface of the metal. So this is adsorption. Okay, and then we call the surface sites of adsorption, we call them active sites. Okay, I think it should be spelled as SITES. Yeah, so these are active sites. Okay, the absorption process brings about reactant closer together. Yeah, so increases surface concentration. Yeah, and in the course of adsorption, the critical covalent bonds within the molecules gets weakened. So this allows an increase in collision via a lowered activation barrier. Okay, so new bonds will be formed between the nitrogen and hydrogen. The final product is, which is ammonia, it is still adsorbed on the surface. Yeah, so you need to give it a bit of time to diffuse away from the surface so that the active sites can then be made available for further reaction to take place. Okay, if you want an energy profile diagram, it will look something like that. The catalyzed pathway should have a lower activation barrier. Yeah, and usually the catalyzed pathway will have several humps. Okay, so in our example here, we just draw one hump, but usually it's just several humps. Okay, which represent the lowered activation pathway, or the pathway with a lower activation energy. Okay, yeah. Okay, do take note of the final term here. I think I have explained that in the kinetics lecture. The term is desorption. Okay, note the spelling because the spelling here is quite important. Yeah, so desorption. Yeah, when you want to describe the process, this adsorption, right? When you say that the molecule adsorb onto the surface, make sure you spell correctly. So adsorb should be spelled as ADSROB. Okay, so it should be spelled this way. This is adsorb. Desorbed will be spelled DESORB. Yeah, make sure you spell correctly. Okay, yeah, so when it's changed to a descriptive term, instead of ADSORB, the B changed to a P, so become adsorption and then desorption. Okay, so remember that. Okay, so I think I don't need to highlight this. I think it's a knowledge most of you are aware of. So the catalyst, not only does it speed up or accelerate the rates of reaction for the forward reaction, it also accelerates the rates of the backward reaction. Yeah, because the forward and backward reaction goes through the same reactive transition states, or the same transition state over here. Of course, for reaction involving gaseous molecules, we do expect the system to have many transition states, not just one hum lah. Yeah, so remember that whatever we present here, right, is just a very simplistic view of the world lah. Yeah, so do remember that. We're not trying to say that it is like that, but we are just using a simplified diagram to explain otherwise relatively complicated concepts. Okay. And then for other heterogeneous catalysts, vanadium oxide, we talked about that earlier on. And then nickel, okay, for hydrogenation. And then I think this is something interesting, the Ziegler-Natta catalyst. I think in the new H2 curriculum, your juniors will learn a little bit about polymerization. Yeah, so titanium chloride with hexyl, ethyl, aluminium, they are able to catalyze the formation of polyethene from ethene. Okay. Next we have 3.2 homogeneous catalyst. The classic example I can tell you, because this is not the first time you have seen this. You have seen it in topic 6 under reaction kinetics, the oxidation of iodides by peroxo disulfates, okay, to iodine and sulfates. Okay, so take note that it doesn't matter whether your catalyst is iron 3 or iron 2. Yeah, if you started with iron 3, then the iron 3 will react with iodide first to generate iron 2, where iron 2 will be oxidized by peroxo disulfates. Okay, if you start off with iron 2, then peroxo disulfate will oxidize iron 2 to iron 3 first. Yeah, so as I said, it doesn't matter which one you start off first. Okay, so based on the above data, the reaction is found to be thermodynamically feasible, but expected to be a little bit slow because the two negatively charged ions causes the reaction to have a high activation barrier. Yeah, you have done this particular kinetic studies before. So for a complete reaction, it takes about 30 minutes to about an hour. Yeah, so that's why it is long enough. The production of iodine is slow enough for you to perform kinetic studies. Yeah, so it's not so slow. It's not like super slow until like it takes like a few weeks, but it's just close to slightly less than an hour. Of course, depends on the concentration of iodide and peroxo disulfate as well. I mean, I hope it is obvious to you. Okay, so everything I say is relative. I mean, relatively mild concentration. I mean, not too high, not too low kind of concentration. Those you expect from the labs. Okay, so thermodynamically feasible, but kinetically maybe not so feasible. Okay, because it involves collision between two negatively charged ions. How can we make it kinetically feasible? We introduce iron 3, which has a positive charge. Yeah, so species which are oppositely charged, they tend to be attracted by electrostatic attraction. Okay, so the reaction is likely to be accelerated. Okay, then again, before we even allow the, before you can even so-called talk about the kinetics, you have to ensure that the thermodynamics variable fits. Yeah, so we need to calculate a E cell. Yeah, and then you notice that for both reaction, the reactions are feasible. You might be a bit confused over here. Why is there a need to calculate E cell? Yeah, because to begin with, we need to ensure that thermodynamically the reaction can take place before we discuss the kinetics component. The kinetics component is the one where we will make a postulate that because iron 3 and iodides, as well as iron 2 and peroxo disulfate, they are oppositely charged. Yeah, the collision involving these two species is likely to be barrierless, okay, or almost barrier free. Okay, so indeed, when we introduce iron 2 or iron 3 into the system, the reaction goes through goes at a very fast rate. Okay. Yeah, so I think we have discussed this. Yep, and then yeah, so normally for a catalyzed reaction, we will tend again similar to what I discussed above, like we tend to draw a few humps. The reason why we drew a few humps is because we want to impress upon the examiner that there indeed there are intermediates present in the course of the reaction. Yeah, and then these are what we call the catalyzed activation energy, the first catalyzed barrier to reach the intermediate, and then the next one is the catalyzed activation barrier from the intermediate to reach the product. Yeah. Are we saying here that the uncatalyzed reaction has only one transition state? Okay, just one? No, we are not saying that. It could have a few transition states, but we are just drawing out again, as I said above. It's just a simplistic view of what is otherwise a relatively complicated reaction in its own right. Okay, yeah. Then for section 3, we are going to look at exercise 3.1. Okay, so over here, the rates of the reactions between iodide and peroxide disulfate is given below. So again, we are looking at peroxide disulfate and iodide. Is increased by the presence of small concentration of cobalt 2+, suggests how cobalt 2 ions are able to participate in this reaction. Okay, so this is quite interesting. Yeah, so in this case, we need to introduce cobalt. Okay, so we need to scroll back. So we are likely looking at the two aqua species, cobalt 3 and cobalt 2, with a reduction potential value of 1.89 volts. Okay, so I'm just going to write it as 1.89 volts. Take note of how you write cobalt, because most of our students will write cobalt as CO and both of them capped. Okay, do take note of that. You are not allowed to cap it. Okay, because if you cap it, it is carbon monoxide, not cobalt. Yeah, so this is plus 1.89 volts. Another thing I thought I just want to make mention to all of you is that this question is actually kind of like, it's a fictitious kind of question, because in reality, cobalt 3 aqueous does not exist. Cobalt 3 is able to oxidize water to oxygen. Yeah, so it is almost impossible for cobalt 3 to exist in the aqua species. Yeah, so usually you need ligands to stabilize cobalt 3 and cobalt 2. Cobalt 2 can exist. Not a problem at all. You have seen some of its chemistry. Yeah, but for cobalt 3, its existence is kind of fictitious. Okay, yeah. Then of course we need what we have earlier on, iodine iodide. Okay, so we just need to copy what we have earlier on, iodine iodide. Okay, so this is plus 0.54 volts. We also need peroxide disulfates to sulfates. Okay, this is 2.01 volts. Okay, yeah. So we will go through the same thought process. Yeah, first of all, because we are given cobalt 2+. Okay, so we will want to check out whether peroxide disulfate can oxidize cobalt 2 to cobalt 3. Okay, shall we do that? Okay, so we will try to calculate the E cell. Okay, so CO 2+ reacts, okay, with S2O8 2-. Okay, so we'll check it out. So the E cell, okay, is E reduction. Okay, E reduction minus E oxidation. Okay, CO3+. Okay, CO2+. Okay, so this will be plus 2.01 minus 1.89 volts. Okay, we are going to get 0.12 volts. Okay, which is greater than 0 volts. Yep, so this reaction is likely to be, it is thermodynamically feasible, and it is also likely to be kinetically feasible. Okay, because it involves the collision between oppositely charged species. Okay, then next we are looking at cobalt 3+. Okay, reacts with I-. Okay, so we're going to check out whether it's feasible. Okay, I'm sure it's feasible. So E cell is E reduction. Okay, E reduction minus E oxidation. Okay, so we are going to get 1.89 minus 0.54. Okay, so we are going to end up with plus 1.35 volts, which is greater than 0 volts. Okay, so therefore the reaction is thermodynamically feasible, and it is likely to be kinetically feasible as well because it involves iodide and cobalt-3. Okay, yeah. Are we going to write a balance equation for the reaction? Yes, of course we're going to write a balance equation. So the balance equation for this will be 2 cobalt 2 plus S2O8 2 minus. I'm going to end up with 2 sulfates, okay, plus 2 cobalt 3 plus. Okay, equals. And then after that, we have 2 cobalt 3 plus equals plus 2I minus equals. I'm going to end up with cobalt 2 plus equals plus I2. Okay, you'll notice that cobalt 2 plus is being regenerated in the process. Okay, we started off cobalt 2 plus being oxidized to cobalt 3, and then cobalt 3 is now being reduced back to cobalt 2. So it shuttles between a plus 3 and plus 2 oxidation states. Yeah, so in the course of this particular reaction, iodide and peroxyl disulfate, they do not meet and react. Yeah, so they react with cobalt 2 and cobalt 3 via their own separate pathway to reach the respective products, and the respective pathways are thermodynamically feasible as supported by the E cell values. Okay, then you might ask, how do you know whether they are kinetically feasible? Okay, so they are likely to be kinetically feasible because it involve, or their reaction involve collision between oppositely charged ions. Alright, so next we're going to move on to section 4 on transition element complexes. You have probably heard of the term complexes many times, maybe as early as after promos last year when we introduced you to some qualitative analysis dry practical. If I'm not wrong, that would be practical 11, 12 and 13. Yep, or if you fast forward January this year, where in the laboratory you have done some QA labs, you probably have heard your teachers talking about this particular PPT dissolved due to the formation of complex. You heard of complex many times. Some of you might read up a little bit about it, or sometimes your teachers might have discussed a little bit in the tutorials with you. Yeah, so for this particular section, it will be a formal introduction to complexes. Yep, and in particular, taking the cue from your learning objective, that will be exemplifying complexes formed between copper 2, water, ammonia, and chloride as ligands. Okay, yeah, so there is also a need for you to discuss transition metal complexes found in the QA notes, although not explicitly. Okay, so what do I mean by transition metal complexes found in the QA notes? So for example, in your QA notes over here, just look at the QA portion. Okay, so you were given, for example, some of the unknown, like chromium 3, the gray-green PPT will be soluble in excess sodium hydroxide to give you a dark green solution. Yeah, so you are familiar with this. So you need to know that the complex form is actually the hexahydroxyl complex. Okay, so it's the chromate complex, CrOH6 3- complex. Yeah, you need to know its formula. And then of course the all-time favorite tetraamine copper 2 complex, you need to know its formula as well. Okay, and then for the solubility of silver chloride in excess aqueous ammonia, you need to know that the complex form is the diamine silver 1 complex. Okay, so these are some of the examples of complex you need to be aware of. Okay, then if I'm going to move into the electrochem reduction potential values given to you, you are also introduced to some complexes. So for example, we have hexaamine nickel 2 complex over here. Yeah, this is in contrast with the hexa aqua nickel 2 complex. Okay, I put them side by side, or it's being put side by side for you. You are also given the hexacyanato complex of iron. Okay, so I put them side by side. You have an aqua complex and you have a hexacyanato complex. Okay, and then of course you have the diamine copper 2 complex over here. So they are being put side by side over the copper, so it's over here. Okay, as well as hexaamine cobalt 2 complex. Okay, it's also being put here. So you can contrast it with cobalt metal. Okay, I think the rest of the complexes are not in your data booklets. Okay, so if needed, then it will be provided for you. Okay, so if we head straight to the definition, a complex is a molecule or ion formed by a central metal ion or atom, okay, surrounded by one or more ligands. Okay, so I think earlier on I have already given you an example of a central atom with an oxidation state of 0. Okay, so for example, the tetracarbonyl nickel 0 complex. Yeah, so this is the complex where the overall charge is 0. Your nickel exists as an atom, and then your carbonyl, sorry, this should be CO. Okay, CO. Your carbonyl is the ligand, which is also a neutral ligand. Okay, do take note that ligand need not be charged. Okay, so ligand can be neutral. For example, ammonia is a neutral ligand, carbonyl is a neutral ligand. Okay, also the overall complex need not be charged as well. Okay, for example, the tetracarbonyl nickel 0 complex is neutral. Okay, in terms of electrical charge. Okay, yeah, so next, this particular portion is definitely not surprising. If I dissolve copper sulfate in water, I'm going to get the hexa aqua copper 2 complex, which exists as a pale blue solution. Okay, so the pale blue solution, this particular complex is responsible for it. Yeah, so you do note that there are 6 water ligand surrounding the copper 2 center. Yeah, and otherwise we call this the octahedral complex. Yeah, so this particular complex is known as an octahedral complex. Most of the complexes you encounter in H2, they are usually octahedral complex if there are 6 ligands. Okay, if there are 4 ligands, then it is either square planar or tetrahedral. Some of you, I can see the questions coming. When is it tetrahedral? When is it square planar? Well, I mean, if you are interested, do take on a higher level course in transition elements. Then I think you will learn a lot more. It's definitely not, these are things we can't cover in a very generic chemistry curriculum. Okay, so do read up more, and I'm sure you'll learn a lot more and appreciate transition metal chemistry much more than organic chemistry. Okay, yeah. The covalent bond form is also known as a coordinate bond or a dative covalent bonds. Okay, so there are different ways of identifying the bonds. Okay, and we normally put a square brackets around. So if I'm going to zoom in, we will normally put the square bracket before the charged. Okay, so there's no mistake about this. Some of you might think that this might interfere with the concentration symbol. Yeah, not to worry. As long as you are clear and know what's going on, I think that should be fine. Yeah, but in general, we will put a square bracket around a complex. Okay, we call them the aqua complex because water is the ligand. Okay, I think we have discussed this. Complex can be neutral, cationic, or anionic. The overall charge can also be anionic or cationic. Okay, so these are the examples. If you want to, you can take note of them. Okay, yeah. And sometimes for complexes, their existence will also mean that there are other counter anions or cations that are present. Yeah. So for example, this particular complex, we call it hexaamine cobalt 3 complex. There will be 3 chloride ligands present. Yeah, and sometimes things can get a little bit complicated because the chloride ligand can also, not chloride, the chloride counter anion can also act as a ligand. So you will get into a situation when the molecular formula seems to be the same, but the different ligands are being interchanged. Yeah, some became the counter anion, some actually is part of the complex, or they interchange, and then things can get a little bit complicated. Okay, I'm sure you'll get some of these in our tutorial, so do take note of them. Okay, yeah, so when we dissolve the tetraamine cobalt 3 complex with the 3 chloride ligands in water, then you're going to end up with something like this in the solid phase. Okay, so this is in the solid phase. Of course, this is just a representation, then the exact details we are not sure. Okay, then of course the ligand remain attached to the central atom. Then some of you might be wondering why water will not replace the ammonia. Yeah, so in general, ammonia tends to be a stronger ligand than water. The reason being ammonia is a stronger base, or ammonia is more nucleophilic at the nitrogen center due to its lower electronegativity value as compared to oxygen. This is in general, okay, it's not always the case. Okay, yeah, so we gave you some reasons why transition metal ions tend to form complex. Okay, so they tend to be stabilized in the complex, and of course the incomplete 3D subshell will be able to welcome lone pairs of electrons from the ligands. Okay, yeah. Then next we are going to move on to 4.2, where we'll be discussing ligand. So in general, ligand, it could be a molecule, it could be an ion, so do ensure that your definition is all encompassing. Okay, so it should also contain one or more lone pairs of electrons available to form a coordinate bond, or to form a dative covalent bond with the vacant orbitals of the transition metal. Okay, so do take note of that. Yeah, and then we classify ligands as blah blah dentate. So if there's only one coordinating site, we call it monodentate. Okay, so one coordinating site, we call it monodentate. 2 coordinating site, we call it bidentate. Some of you might be wondering, why not didentate, right? Okay, so these are all legacy issues. So historically, organic chemistry and inorganic chemistry, they tend to be studied separately by different groups of people. So each group of people develop their own terminology, quite similar, and yet there's some differences. So I guess you guys just have to accept the difference when you are studying inorganic chemistry. Okay, of course now chemistry is one whole discipline. I mean, we do talk to each other very often, and you guys learn them in a broad-based curriculum like H2, but yeah, do take note that there are some difference in terminology. Okay, anything beyond bidentate, we just call them polydentate. In case you are wondering, what about like 6? Yes, 6 is still called hexadentate. 4 is tetradentate. Okay, not quaddentate. Okay, this is tetradentate. Yep. So polydentate ligands, they tend to be called chelating agents. This is a very interesting term, chelates. Yeah, sometimes we say that polydentate ligands are stronger than monodentate ligands due to an effect known as the chelate effect. It has been studied for over a century, and it's almost a Nobel-winning work. So if you want to, you can study more about the chelate effects. Yeah, so there were also discussion on whether chelate effect is thermodynamic in origin or entropic in origin. Okay, so you can read more about them, and then I think it will build up your arsenal and understanding regarding transition metal. Okay, so over here we have some examples of monodentate ligands. You are familiar with most of these ligands. I think water is okay. Ammonia. Okay, so chloride is not an issue. Yeah, cyanide, carbon monoxide, thiocyanate ions, they tend to be much stronger ligands as compared to water, ammonia, and chloride, as well as hydroxide. Okay, there's a reason behind, but I'm not going to discuss. Okay, so if you're interested, you can read more about pi back bonding. Okay, pi back bonding. Yeah, so they have another name as well. They are known as pi acids, but again, I'm not going to go into details because it's absolutely not required for H2. Okay, by dentate ligand, there are two coordinating sites. So what are the two coordinating sites? So over here, the two amino, and then glycinates will be NH2 and carboxylates, and then ethane diol will be this and this. Okay, and then we have a hexadentate ligands. Where are the coordinating sites? It's over here, 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 and here. Okay, so altogether 6 coordinating sites. Okay, 2 from the tertiary amines, 4 from the carboxylate anion. So this is known as EDTA. It is a drug we take in whenever we are suspected of having heavy metal poisoning. Okay, because it is able to form chelate or complex with the heavy metal, and then you can flush it out of your body. Okay, yeah. Then we have 4.3 on coordination number and geometry. Okay, again, can I stress that this is really very simplistic. We are not going into great details. There's whole modules on coordination chemistry alone. They took about 4 to 5 months to complete. Okay, so do bear with me if we are just going to just touch and go. Okay, that is the case for H2, unfortunately. Okay, yeah. If you are thinking about relating them to the valence shell electron pair repulsion theory, I would say no, don't do that. It has almost no relation with valence shell electron pair repulsion theory. Okay, so we are not talking about VSEPR over here. Okay, so we are not talking about this over here. Okay, yeah, so we have talked about the diamine silver 1 complex, coordination number 2, so it's a linear shape. Okay, this particular complex you're probably not familiar with, the tetracyanonickel nickel complex with 4 coordination. It's a square planar complex. Okay, but the tetrachlorocopper 2 complex is tetrahedral in shape. Yeah, it is actually fluctuating between tetrahedral and square planar. So the actual shape is in between, but by and large, we just take it to be a tetrahedral complex. Okay, yeah. I mean for H2 that is lah. Yeah, and then of course octahedral complex. Example, you are aware of it. The one involving water ligands with 6 water ligands around iron 3, iron 2, copper 2. Yeah, octahedral. Yeah, over here we are giving you another flavor. We are giving you an iron 3 complex with 6 cyanide ligands. So this is an octahedral complex. Okay, yep. And then the geometry, this is not in the syllabus, so we don't need to discuss. It's basically it's based on the stability of the central atom with regards to the complex. With regards to the ligands. Yeah, so the nature of the ligand will swing the complex from tetrahedral to square planar. So there has been many studies on it, but again, not in H2 curriculum, so we don't delve into great details. Right, so next we have exercise 4.1. Okay, for question 1, you are supposed to complete the missing information in the table below. Okay, so we have a chromium complex here, okay, with 6 cyanide ligands. Okay, so what is the oxidation number of the central metal ions? We can easily do a calculation and determine it to be +3. Okay, so this is not very difficult. And then for the copper 2 complex over here, okay, so I think we'll go in horizontal fashion. Okay, so number of ligands will be 6 ligands. Coordination number will be 6 as well, because there are 6 coordination sites. Okay, and then overall charge is -3 is given to us. Okay, then over here we have 4 ammonia ligand, 2 water ligand. Okay, so we have coordination number of 6 as well. So what is the net charge of this particular complex? So it's +2, we are familiar with this. And then of course oxidation state is +2 as well. Okay, some of you might be wondering, for the longest time we have been calling the complex tetraamine copper 2 complex. Why is there 2 water ligands sometimes being written? Okay, so some of you might question the legitimacy of the 2 water ligands. Okay, the 2 water ligands is actually weakly binded to the copper 2 center via in the axial direction. Okay, so basically this particular complex looks like this. You have the ammonia ligand with a copper, another ammonia ligand over here, another ammonia ligand, and another ammonia ligand. Okay, it's a square planar complex, okay, with a +2 charge. Okay, yeah, the water ligand is very weakly binded to the center. Okay, so it's very far away. Yeah, so this axial bond is very much elongated, so it's a very long bond. Yeah, so some school of thoughts feels that we should not include these 2 weakly binded water ligand as part of the complex. Other school of thought say it should be in. So it's basically the 2 parties are fighting against each other. Yeah, so my personal school of thoughts shouldn't include, but of course sometimes exam question does include that in. If it includes, then you just have to I mean you just have to put it in. I mean it's not a big deal. Okay, yeah, I mean I hope that just explain it, and you guys knows what exactly is going on. I think that is most important. Okay, yeah. Next we have the oxalic complex involving iron 3. Okay, because oxidation state is +3. Okay, so obviously we count here there are 3 complex per metal ions. Okay, the coordination number will be 6 as well. Yeah, because obviously each of the oxalic ligand, so this is an oxalic ligand, it looks like this, O minus, okay, C double bond O, okay, and then a double bond O and an O minus. Yeah, so this is the ligand originated from oxalic acid, or what we call ethane dioic acid. Okay, so there are 2 coordinating sites over at the oxygen bearing the negative charge, and altogether the number of coordination number is 2 times 3, so that will be 6. Okay, and then for example, and then the last one we have the EDTA. Yeah, earlier on we know that the EDTA has a -4 charge, and then of course the central copper 2 is +2, so overall charge will be -2. Okay, and then number of ligands will be 1. Yeah, so because earlier on we have EDTA as an example here, so its binding site will be via the 2 tertiary amines as well as the 4 carboxylic anion. Okay, yeah, gonna move on to the next example. Okay, question 2. Yep, so we have a complex is obtained by reacting cobalt 3 chloride with ammonia. It is found that the coordination number of cobalt is 6, and that only 1/3 of the total chloride is precipitated as silver chloride when the complex is treated with excess silver nitrate. What is the formula of the compound? Okay, so first of all, we need to be very clear. Okay, so for cobalt chloride, its formula would be COCl3, because cobalt is in the +3 oxidation state. Okay, so when we dissolve it in ammonia, we were told that the coordination number of cobalt is 6. Okay, and that only 1/3 of the total chloride is precipitated as silver chloride. What does it mean? Okay, so for every 1 equivalent of cobalt chloride I dissolve, I'm going to produce okay, so let me just try to, it's as a thought process. This is not exactly a reaction, okay, so it's a thought process. I'm going to produce 1 equivalent of cobalt 3 and 3 equivalents of chlorides. Okay, yeah, so I'm told that only 1/3 of it can be precipitated as silver chloride. Yeah, so that means that out of these three, two of it, so 2Cl minus coordinates, okay, coordinates, or rather, maybe I make it much simpler. 2Cl minus are ligands, okay, coordinating to cobalt 3. Okay, does that make sense? Yeah, because those chloride that can be precipitated out when I add silver nitrate, they are found outside the complex, so they are what we call existing as free chloride ions. Yeah, so therefore 2 chloride will be part of the complex. Yeah, so if 2 chlorides are part of the complex, that means that my complex must have 1 cobalt, 2Cl2. Okay, okay, I'm writing it in a very ugly fashion, but it doesn't matter, because at the end of the day, this is, we want to solve the question first. Okay, so I'm just writing it as I think about stuff. Okay, so we have 2 chloride ligands, as well as 4 ammonia. You might be asking, how do I know there's 4 ammonia? Well, the question said that the coordination number of cobalt is 6. Well, so 4 ammonia, I mean, that makes sense, right? Yeah, and then this is the complex, right? And then, of course, it will take on a plus charge because cobalt is plus 3, Cl is minus 1, and then we have a chloride outside. Okay, so that makes perfect sense. Okay, so therefore, the formula of the compound, if I'm going to choose from the list, it will be C. Okay, does that make sense to you? Okay, because again, why do I choose C? Okay, because as I said earlier on, it must contain 4 ammonia ligands and 2 chloride ligands. And why is that the case? Because I'm being given this very important hint. 1/3 of the total chloride is precipitated as silver chloride. Okay, yep. So with that, we have completed this particular exercise 4.1. Okay, so we'll move on to 4.4. Yeah, 4.4 again, let me repeat, it is not something which is very complicated. You would have heard your teachers talking about them when we are teaching you the QA. Okay, you do know that some of the aqua complex are mildly acidic. Yeah, because they undergo a reaction, we call it hydrolysis. Hydrolysis is actually a dirty word in chemistry because it seems that everything also hydrolysis. Okay, yeah, so you need to know how to differentiate the term hydrolysis between different reactions anyway lah. Okay, so they will give us a mildly acidic solution. So for the hexyl aqua iron 3, it will ionize partially to give us a little bit of H3O plus, and then chromium 3 as well to give us a little bit of H3O plus. Yeah, so in general, this is actually due to the high charge density of the central ion. Okay, so based on what you have learned, there are 3 in total within your H2 curriculum: aluminium 3, iron 3, and chromium 3. Okay, so these are the 3 metal cations which have high charge density, and you need to be aware of the acidity of their aqua complexes. Okay, yeah. Then you might be asking, what about +2? Are they totally not acidic? No, this is not true. They are very slightly acidic, but usually we don't want to make a big hoo-ha out of it. Yeah, so if you don't believe, copper 2 is actually a little bit acidic. Yeah, in all honesty, just a little bit acidic. Yeah, you can use a litmus to verify that. Okay, yeah. Next, okay, any metal with a greater oxidation number than +3, they will usually form oxo anions, as what we have discussed earlier on. Like for example, for permanganate and dichromate, they will form what we call polyoxo anion, because the metal oxygen double bond helps to stabilize the high charge of the, or high oxidation state of the metal. Okay, yep. Chromium complexes and oxo ions. Okay, so there is a little bit of focus on chromium complexes over here. So let us discuss a little bit. I think we have seen this in our lab. If not, you can we'll have a video for you on the QA experiments which you can view. Okay, yeah, so when aqueous hydroxide or aqueous ammonia is added dropwise, we get a gray-green precipitate. Okay, so you need to take note of this gray-green precipitate. Many students mistook the dirty green PPT of iron 2 as gray-green for chromium. Okay, so I think you have to observe a little bit carefully. They are quite different. Okay, so this is due to the formation of chromium 3 hydroxide. Okay, yep, so it's actually an acid-base reaction, or you can view it as a precipitation involving chromium 3 and OH minus. Yeah, so there are a few aspects you can look at. Doesn't really matter. Okay, and then when sodium hydroxide is added in excess, we get a dark green solution. This is a dark green complex being formed. Okay, it also demonstrates the N4 theoricity of chromium 3 hydroxide. When acid is added to yellow solution of chromate 6, okay, so this is chromate 6, do take note of it. So this is the yellow chromate 6 over here. Okay, it will lead to the formation of dichromate 6, which is orange in color. Okay, so this is dichromate 6. Okay, and in the process it loses one water molecule. Yeah, so from here I think you can roughly tell that when acid is added to chromates, water will be driven off and it will lead to the formation of dichromate, which has a bridging oxygen atom, or you can view it as a ligand, but it's actually more of an atom. How does dichromate looks like? Okay, so dichromate is something like that. You have an O here, and then you have an O minus, okay, and a double bond O, and then you have a bridging oxygen, and then another chromium, and then double bond O, and then O minus. Okay, so this is how dichromate looks like, and I don't think it stops at dichromate. It will continue on and on to give you give you an oligomer. We call that an oligomer, which means a few water molecules will be given off along the way. Yeah, but again, we're not going into great details on that because that has been widely studied in the past. Okay, but just take note that it doesn't stop at the dichromate. It can be controlled. Okay, but you do not really learn them in the H2 curriculum. Okay, yeah. Then 4.5, we have ligand exchange. Okay, so what exactly are we dealing with for ligand exchange? So basically, in short, a stronger ligand will displace a weaker ligand. Okay, so for example, when we are adding thiocyanate to iron 3, we get a blood red complex. Yeah, so this particular blood red complex is characteristic of iron 3. Okay, of course, it's not purely iron 3. Okay, it's basically one of the thiocyanate ligand displacing one of the water ligands. Okay, why is it that the complex, the color changed from yellow to blood red? Okay, so this is something not within the scope of the H2 curriculum as well. Although you might learn a little bit from the color section later on, but that one is a very simplistic view. Yeah, so if you want to learn more, yeah, please really study what we call the ligand field theory, and then know about things such as metal ligand or ligand metal charge transfer, or more about DD transition, and how the break in the symmetry of the complex will lead to either a widening or narrowing of the homolumo gap. All this, yeah, it's really complicated, so we will not go into details. Of course, there are some simplifications inorganic chemists came up with, but we won't discuss too much of it. Okay, yeah, so there will be a color change, and it's represented by the following equilibrium constant. Okay, so you notice that the equilibrium constant, when we write in the square brackets for the representing the concentration term, yeah, we do not put the square bracket as a square bracket representing the complex. Yeah, so whenever we are writing equilibrium constant for complex formation, we will ignore the square bracket for the complex. If not, then there will be two square brackets, which make life quite complicated. Okay, which will confuse you as well. Okay, yeah, so because water is the ligand, is also a solvent, so concentration of water is a constant, so it's not involved in the Kc expression. I think we learned that in the topic on chemical equilibrium. Okay, yeah. So the Kc is large. It is likely to be very large, so the reaction will be driven to completion. Okay, so usually we represent with a single arrow over here. Okay, yeah. And then ligand exchange involving copper complexes. Are we familiar with this? Yes, we are extremely familiar with this. We have seen that many times. I've explained that in quite a number of QA videos as well. Okay, so the formation of copper 2 hydroxide. Okay, so this is what we know. And then the ligand exchange to form the dark blue solution. Okay, and then how the formation of the dark blue complex will cause the position of equilibrium of the dissolution of copper 2 hydroxide to shift to the right, which result in what we observe as pale blue PPT dissolve in excess ammonia to give us a dark blue solution. Okay, in the past we call this a deep blue solution. I think now it's called dark blue solution. Okay, likewise, when we add concentrated hydrochloric acid to copper 2, we are going to get a yellow complex. Yeah, so normally in quite a number of cases, we don't really observe the yellow complex. We will observe it more as a green complex, because normally what we observe is an equilibrium or a mixture of hexa aqua copper 2 as well as the tetra chloro copper 2 complex. Yeah, so we normally will observe it as green. Yeah, in order to get the yellow complex, we need to ensure that we use very dilute solution of copper 2. Then we need to add in concentrated hydrochloric acid. Okay, and then this will ensure that the equilibrium position will be pushed towards the tetrahedral complex. Okay, yeah. I think it's explained here. The green color is due to the presence of both the aqua and the chloro complex. Okay, yeah. An application example here, effects of ligand exchange on reduction potential. Taking a hint from the data booklets, we have written down the standard reduction potential of two iron 3, iron 2 species, one with water as the ligand, the other one with cyanide as the ligand. You'll notice that the standard reduction potential reduces from 0.77 to 0.36 volts. What is the implication of this? Okay, so the implication is that we are aware that iron 3 can oxidize iodide to iodine. You would have seen this in your laboratory work or the tutorial examples. Yep, so when we perform a calculation of the E cell involving hexa aqua iron 3 and iodide, we get a positive E cell which is greater than 0 volts. So we'll be able to conclude that the reaction is thermodynamically feasible. However, right, if we are going to use the one with cyanide as the ligand, we will get a negative E cell. So that means that the reaction is not feasible. Yeah, so from here, you can tell that changing the ligand from water to cyanide is able to affect the reactivity of the iron 3 towards a reducing agent such as iodide. Yep. We can delve a little bit deeper into the values if you wish to. Yeah, from here, right, I'm not sure whether you guys can tell, but are you able to tell that cyanide stabilizes the iron 3 oxidation states, or iron in its plus 3 oxidation state more than iron in its plus 2? Okay, I'm not sure whether you can agree with me on this particular statement. If cyanide stabilizes both iron 3 and iron 2 to the same extent, then there shouldn't be a change in the standard reduction potential. If it stabilizes iron 3 more than iron 2, then it will lead to a reduction in the reduction potential value, as what we have seen in this particular case. Okay, however, if it stabilizes iron 2 more than iron 3, then it will lead to a widening in the reduction potential value. So that will means that it will be greater than 0.77 volts. If you are not sure what I'm talking about, you can think about it and then we can discuss more during our tutorials. Okay, We will next move on to 4.5.3 regarding ligand exchange reaction in hemoglobin. Okay, this is a little bit bio-like. Again, we will not go into details, but we are just it's more of an awareness kind of thing. Okay, so what we need you to recognize is that oxygen is the ligand attached to iron 2 in hemoglobin, and oxygen binds very weakly to the iron 2 center in hemoglobin. Okay, so for hemoglobin, we can take a look at this particular protein structure. Yeah, so basically it contains the heme group. The heme group is a tetradentate ligand. Okay, so it consists of the 4 nitrogen center, okay, as exemplified by this. Okay, yeah, and below there is histidine coordinating to the iron from below, right? So this is what we call a pans dentate ligand. Then at any one point in time, there will be a 6 ligand coming in. So the number 6 ligand is either oxygen, or most of the time is oxygen. Yeah, and oxygen has to bind weakly to the iron 2 center. Why is that the reason? Because the purpose of hemoglobin is to transport oxygen around the body. Yeah, so that's in a region where oxygen is deficient, then the oxygen will diffuse into the necessary organ in order to supply it with oxygen. If oxygen binds too strongly to hemoglobin, then the system will require too much energy to drive the forward reaction. Yeah, so the weak binding of oxygen onto hemoglobin is a must. Yeah, however, it is also one of the most fatal points in evolution, because carbon monoxide actually binds close to 200 times stronger than oxygen. Yeah, because of the strong binding, it is very easy for us to be poisoned by carbon monoxide, or for us to get carbon monoxide poisoning. Yeah, so once we get carbon monoxide poisoning, then all the oxygen will be replaced, and the species form, which is what we call the carboxyl hemoglobin, is a very stable species. Yeah, and oxygen will not be able to displace carbon monoxide as the ligand. Yeah, so you need to go through oxygen therapy in order to recover, and sometimes once your brain or important organs gets cut off oxygen for, say, longer than, I don't know what's the medical term, maybe 5 minutes or 10 minutes, yeah, then it will lead to brain dead, or will become will be in the vegetative state. Yeah, so a lot of things can't function. A lot of parts in our body can't function when we are deprived of oxygen. Yeah, so as to the reason why carbon monoxide binds extremely strongly to iron 2, yeah, so I think this reason we can explain it in the tutorial. Yeah, basically CO, as I mentioned earlier on, is a much stronger ligand than oxygen. Is because CO as a ligand, right, it is known as a pi acceptor ligand. Okay, what exactly is a pi acceptor ligand? You need to understand a little bit of molecular orbital theory in order to appreciate that. Yeah, so basically for carbon monoxide, when it binds to the iron center, right, it binds through the carbon. Okay, this is a dative covalent bond being formed, and at the same time, right, it is able to form what we call a pi back bonding with the d orbitals in iron 2. Yeah, so this kind of bonding is what we call a synergic kind of bonding, because it's like the carbon donates to the iron 2 center through the dz square orbital, and at the same time the electron rich d orbital of iron 2 will back donate electron density back into the CO pi orbital. But in the case of the pi orbital, CO is actually the pi star. Okay, the anti-bonding pi orbital. Those of you doing H3, you'll be familiar with it. For those of you who don't really understand what exactly is pi star, or the molecular orbital theory of, you might want to read a little bit more so that you can appreciate a little bit more why CO is a stronger ligand than oxygen. And also, if you are able to understand molecular orbital theory, you will understand why oxygen binds in a slanted fashion. Yeah, so oxygen does not bind in a linear fashion. It binds with an angle of 109 close to 109.5, or actually close to 120 degrees. Yeah. Yeah. So you can ask your friends who did H3. They will be able to they will be able to explain to you why. Yeah, because the highest occupied molecular orbital of oxygen is actually lying in a pi star, and pi star, it has this particular shape. Okay, so that's why it binds in a tilted fashion. Okay, so yeah, if you don't understand whatever I mentioned, never mind. I think it doesn't really matter. It won't affect your learning. But what is more important is to appreciate the fact that CO is a stronger ligand than oxygen, because CO is known as a pi acceptor ligand. Okay, so it's spelled as pi acceptor ligand. Okay, yeah. So we're gonna move on. You might want to maybe have a brief understanding of how does oxyhemoglobin looks like. Okay, so if you take a look at figure 5, I think you can appreciate a little bit more. If not, then I think it is okay. You can just skip the biological part. Basically, if you don't know what this is the protein. Okay, this whole group is the protein surrounding the heme group. Okay, yeah. Then section 5, we are going to look at colored compounds and complexes. Okay, yeah. So transition metal compounds are often colored. Why is that the reason? We're not going to go into physics, but basically it's good to understand the color wheel. Okay, so in the visible region, the range will be from 400 to 700 nanometers. Yeah, so close to 400 you appear as violets, close to 700 nanometers it will appear as reds. Yeah, so usually the color of a complex, you can observe that particular color is due to the fact that the complex absorb lights of opposite wavelength from the color wheel. So for example, if a complex appears red in color, okay, let's say it appears red in color, then you expect it to absorb between 480 to 560. Okay, yeah, so that's what we call the complementary colors. Yeah, and we can go through a little bit about on physics here. So the energy of the light is inversely proportional to its wavelength. So you can view it as E is equals to hc over lambda. So h is the Planck constant, c is the speed of light, lambda is the wavelength. So the energy is inversely proportional to the wavelength. Yeah, so the shorter the wavelength, the larger the energy gap, okay, between the HOMO and LUMO. But we don't go into HOMO, LUMO, we just talk about the energy gap. And later on, you will learn that the energy gap is the gap between the splitted sets of d orbitals. Okay, yeah. And what we are looking here is the crystal field theory. It's a very simplified theory. When you go to university, you will learn something more advanced. It's known as the Ligand field theory. Okay, so we assume that the ligands are point charges, okay, attracted to the central metal ions. Okay, so they also repel, this is important, electrons in the d orbitals of the metal ions. Okay, yep. So there is a need for you to know how to draw the 5 sets of d orbitals. Yeah, so a quick revision: d, y, z, x, z, and xy, they lie along the plane being defined by the axis. Okay, and they do not lie along the axis, but 45 degrees from the axis. Okay, so d, y, z will be along the yz planes. Yeah, but the orbital loop is pointing 45 degrees from the yx or yz axis. Okay, yeah, same goes for the other two. And dx square minus y square, basically it is the dxy rotates by 45 degrees clockwise or anti-clockwise, and the orbital loops lies along the axis. Okay, so that will be dx square minus y square. dz square will be the loop lying along the z-axis with a donut shape around the xy plane. Okay, yeah, so it's good to understand the 5 sets of 3D orbitals, because when you are studying transition matter, this particular topic, if you don't really understand or remember the shapes of these 3D orbitals, then you will get a bit confusing later on. Okay, yeah. So how does this leads to the splitting of the degenerate d orbitals in the octahedral complex? First bullet point, basically in free transition metal ions, all the 5 d orbitals are degenerate. Yeah. Then when a ligand is present in an octahedral field, we talk about the octahedral field by saying that in an octahedral field we have ligands approaching from both sides of the 3 axes. Okay, because of that, if you take a look at this, when it approaches along the axis, do you notice that those 3D orbitals that are along the axis are repelled to a greater extent? That is 3x squared minus y squared and 3z squared. They are repelled to a greater extent as compared to the electrons in the d orbitals are occupying dyz, dxz, and dxy. Yeah, so if you are able to understand that, then you'll be able to understand why they are splitted into 2 sets of energies. Okay, so with dz squared and dx squared minus y squared at a slightly higher electronic energy as compared to dxy, dyz, and dxz. Yeah, so this is what we call an octahedral field. There are many kinds of splitting. We will not go into details. For example, in tetrahedral complexes, tetrahedral complex is split into this pattern, so it's exactly opposite that of octahedral, and the splitting of tetrahedral complexes is about half that of octahedral complex. I know you guys will be asking why is that the case. Okay, so you can read up more. Okay, so it's important. I'm just telling you that there are many interesting aspects of transition metal which you can go into, so do read up more beyond the H2 curriculum to satisfy your own curiosity. And square planar complexes are split into this particular manner, so you have 4 below and 1 on top. Okay, something like that. Yeah, okay, yeah, so I will not go into further details. We might talk about some of them during tutorials, but yeah, that's pretty much about it. Yeah, so what exactly is DD transition? So for example, we have titanium 3+. Okay, so it appears purple in aqueous solution. So titanium is a D1 ion. Yeah, so normally we'll call the transition metal ions what kind of ions are they? Are they D1? D1 means it has 1d electrons. Okay, yeah. So when this particular electrons residing in the lower set of 3D subshell absorb energy equivalent to the energy gap, it will undergo electronic transition to the higher sets of 3D orbitals. Okay, so this is known as electronic transition. Okay, I think colloquially we can just say that it jumps from the lower energy level to a higher energy level, but the proper term is that the electrons undergoes electronic transition, okay, into a higher energy level, electronic transition. Okay, there is no in between. Okay, it definitely have to absorb energy equivalent to this. Anything less, nothing's going to happen. Anything more, nothing's going to happen as well. Okay, must be quantized. Yeah, so this comes as a packet of energy. So those of you doing physics, you know what it means. Okay, yeah. So the complementary color of the red, orange, blue light are being transmitted. Okay, so it will appear purple. Okay, so you notice that what's given in this particular bullet point is that the energy gap correspond to the green yellow region. Okay, so if I go back to the color wheel, if it is in the green around this particular region, then the complementary color is violet, so that's why it appears as violet. Yeah, so if you ask me, is it important to remember the color wheel, I would say not the most important, but it will be good to remember it. Yeah, and it's easy to remember the rainbow colors, and I hope the rainbow colors can help you remember the color wheel. Okay, yeah. So I think this is the way it should be explained. In the presence of ligand, partially filled 3D orbitals are split into two slightly different energy levels. Okay, so the energy gap is delta E. Okay, then if the energy equivalent to the energy gap is being absorbed by electrons residing in the lower set of 3D orbitals, then you undergo electronic transition and you'll be promoted up into the higher set of, or the group of d orbitals with a higher energy. Okay, so what you observe, the color you observe, will be complementary to the wavelength of the light being absorbed. Okay, yeah, so that's about it. What affects the color of the complex? Actually, many factors. One of the factors is oxidation states. Okay, yeah, so you notice that scandium 3 plus, titanium 4 plus, copper 1 usually appears as white in the solid phase. Okay, and zinc 2 plus is colorless in the aqueous phase. They are colorless because they do not contain d electrons. Yeah, so do not contain d electrons means they are either d0 or they are d10. Okay, so d10 simply means that the 5 sets of d orbitals are already filled. Yeah, so electronic transition is still possible, so this can go higher. Yeah, but that particular transition will likely occur in a region where it's invisible to the human eyes, so that's why it appears as colorless. Okay, yeah, but one of the misconceptions students have is that, does it mean that all the d0 and d10 metals ions are not colored? The answer is no. For example, potassium permanganate, okay, MnO4 minus, and potassium dichromate, Cr2O72 minus. Okay, potassium, the manganese in potassium permanganate has an oxidation state of +7. Chromium is +6. Yeah, but they are brightly colored. Yeah, one is purple, the other one is orange. Yeah, they are all, both of them are d0, but why are they brightly colored? Yeah, so another mechanism is at play. This mechanism is known as charge transfer. Yeah, so usually charge transfer gives rise to very brightly colored complexes, but not in syllabus, so don't really need to worry about it. Okay, yeah, so the nature of the ligand will affect the energy gap as well. So for example, for hexa aqua nickel 2 complex, okay, the gap will widen if I substitute water with ammonia ligands, and it will widen further if I substitute with ethane diolate ligand. So ethane diolate looks like this, H2N, and then with CH2 and then NH2. Okay, so with ethane diolate, the energy gap will widen. Yeah, so again, two important factors: oxidation states and the nature of the ligand. Okay, so do remember them. They will come in very useful when the time comes. Okay, then 5.4, is there a need for us to remember all the colors? Very common question. Okay, so what I'm going to share with you is, no, there isn't a need for you to remember them because you know most of the colors already. Why is that the case? Because in the laboratory, you'll be familiar with chromium 3 as green, okay, Mn2 as close to colorless, MnO2 as dark browns, permanganate as purple. Some of you might have remembered that when you perform mild oxidation using MnO4 minus in one of the experiment, you notice that you get quite a brightly green colored solution. Yeah, that is actually due to manganese 6. So you have seen this before as well. Iron 2 needs no introduction. Okay, iron 3 needs no introduction. You have seen them. Iron 2 hydroxide is a green PPT, you know it. Iron 3 hydroxide is a reddish brown PPT, you know it as well. The blood red complex is very characteristic of a test for iron 3 using thiocyanate, because iron 2 will not be able to give you a blood red complex. Okay, copper 2 is pale blue, you know about it. Tetraamine copper 2 complex is a dark blue solution, you know it. Tetrachloro copper 2 complex is yellow. You might have seen it before in the lab. not. Yeah, if not, then it's fine. Okay, it's yellow in color, and then copper 2 hydroxide is pale blue PBT. Okay, you see, you know most of it. The only pair you have not encountered, yeah, because we try to avoid letting the students handle chromium, is dichromates and potassium and chromates. Okay, so orange and yellow respectively. So if you ask me, is there a need to memorize? I think my answer to you is most of them you would already know them. So there is a need for you to memorize line by line. Okay, so don't do that. If you don't have time, just forget about it. Yep, and this is an important qualifier. I think I mentioned it to you just now. Not all colors are due to DD transition. There are other kinds of electronic transition. Example, metal ligand charge transfer and ligand metal charge transfer. Okay, if you are interested, please read about them. If not, it is perfectly fine. Okay, yep, and we are at 5.5 now. Okay, using colorimetry in experiment. So again, this is for planning, determining the concentration of complex ions by colorimetry. Okay, so this is one of the planning question, 2013 paper 2, question 1. Okay, yep, so basically you need to plot a calibration graph or a calibration curve. Is first obtained by measuring the absorbance of a series of solution containing the color complex at different known concentrations. Okay, and then after that you can measure the absorbance of the unknown solution and read its concentration of the calibration curve. Okay, so what does it really mean? Okay, so basically what we are trying to say here is that we will prepare known concentration. So for example, it's 0.4, say 0.8, 1.2, 1.6, and then 2. Okay, so so basically you put it into a UV spectrophotometer, and then off the UV spectrophotometer you get a reading. So let's say this reading is A1, and then let's say another reading here is A2. Okay, and then after you start to plot these few lines, I mean these few points, sorry. Okay, I'm just going to erase this to make it clearer. Okay, then after that I'm going to plot what we call a calibration curve. This is known as a calibration line or calibration curve. Yeah, so the assumption we made here is that when we plot a straight line, right, we assume that up to this point, if I have concentration anywhere between 0 to 2, it should obey this particular straight line. Yeah, so if I have an unknown concentration, okay, I put it in the UV spectrophotometer, and I get an absorbance of, let's say, A prime. I should be able to indicate it here, and then go through a dotted line, touch the axis here, touch the graph over here, and then drop another dotted line over here and determine the concentration of the unknown solution. Yeah, so we need to plot what we call a calibration curve first. Okay, you can read through the generic procedure and get the details from the solution we're going to upload for the planning question. Yeah, this is just a generic procedure we're going to provide you here for you to understand a little bit more about what exactly is going on if you're going to do planning. Okay, yeah, so of course earlier on I mentioned the UV spectrophotometer, but in most cases, because this is not exactly in our syllabus, they will use a colorimeter. Okay, so for a UV spectrophotometer, you need to make sure that your absorbance reading is measured at a fixed wavelength. Okay, the reason why this is the case is because normally for absorbance, right, it will let's say I'm going to draw a graph out. It will be something like this, and then it will absorb at one of the, and it will absorb over a range. Okay, maybe I should draw a nicer graph. Okay, it will absorb something like this. Okay, like this. Okay, so this is the wavelength. Yeah, so technically speaking, this is the height, so this is the magnitude, so this is the A. Okay, so technically speaking, we can take any of this point, but normally we will just fix our wavelength. So we will first need to carry out a test in the UV spectrophotometer to get this graph out, and then from the graph we need to determine the maximum absorbance of that particular complex. So let's say this is lambda naught, And then yeah, so usually for lambda naught we already know the concentration, so let's say it's 2 moles per dm cube. Okay, and then we'll get this absorbance, that's called A naught, and then we'll be able to plot this particular point. And then after that, I do not need to repeat this graph. I mean, if I want to, I can repeat this graph at 1.6, 1.2, 0.8, and 1.4, and then I will just meticulously look at where is the absorbance at x naught, etc. Yeah, but if you are using modern UV vis spectral photometer, right, you can just program the machine such that it's able to read off at that particular wavelength, and you will be able to get the absorbance straight away. Okay, so that actually saves you time from just reading off the graph one by one. Okay, because it takes a bit of time to plot the graph even with the machine. Okay, yeah. Then we can also investigate the stoichiometry of complex ion by colorimetry. So the formula of a complex ion can be determined by the color intensity. Okay, so for example, iron 3 with thiocyanates. Okay, so we're going to get a deep red blood complex. Okay, so what we are going to do is we are going to mix them in different proportion. So for example, 10 to 0, 9 to 1, 8 to 2, and then all the way. So so it's kind of like we are just mixing them in different proportion, and eventually we're going to see what is the actual proportion in iron 3 and thiocyanate in their reaction stoichiometric ratio lah. Yeah, so over here it's just 1:x, but we just want to verify that it is indeed 1:1. Okay, and then from here we have different tubes, and then we get the absorbance. These are just arbitrary values, okay? Yeah, I mean they are made up. So in actual fact, it's not like that. Okay, so we get some over this range, and then we're gonna plot an absorbance against the volume of thiocyanate added, or we can also reverse plot it volume of iron 3, and then we get a graph something like that, and then we can just drop down over here. And then you'll notice that the 5:5 ratio gives us the largest absorbance. This actually tells us that the concentration of the complex is at its highest. So that is why the absorbance is the highest. Okay, yep. And then yeah, so you just extrapolate. I think a graph of this nature should not come across as a huge surprise to most of you. Of course, if the ratio is, let's say, I mean, I just give you an arbitrary ratio. Let's say it's 2:4, for example. Let's say it's 2:4. Then I expect the graph to have a shape that looks something like that. Oops, something like that. Okay, you'll be tilted towards in favor 2:4. Okay, yeah. So I will not attempt to draw more things here because it will get a bit confusing. Okay, yeah. So oh, I think I've already explained I mean, inevitably or without knowing, I have already explained the molar proportion of the mixing is 1:1, as what I've explained earlier on. And then in this case, for the balance equation, so I will expect it to be simply just writing out the hexa aqua complex ligands. Hexa aqua complex, and then plus SCN minus. Okay, and then I'm going to get Fe bracket H2O 5 SCN, and because this is minus, remember to reduce the charge to by 1. Okay, so it's 2 plus now, so plus H2O. Okay, this is the expelled ligand. Okay, yep. Then 5.6, we have the procedure of qualitative analysis. So you may be asked to plan a sequence of test tube reactions to identify inorganic ions. Okay, so you have done this, I think, once or twice. So please review what you have learned from the lectures and the laboratory work, as well as to review some of these reactions from your QA notes, especially ionic precipitation, acid-base reaction, redox reaction, and complex formation involving ligand exchange. Okay, so when you plan separation, you may be asked to present your data in a sequence of steps. You may use flowchart or table, Personally, I would prefer table to flowchart, but yeah, it's up to your preference. And then state the positive negative test and include some details, like for example 1 cm depth of the unknown Fa1s. Okay, so for example, in our hypothetical scenario, we have Fa1 containing 2 cations, iron 2 and zinc 2, and then sodium hydroxide and aqueous ammonia are normal test reagents. Okay, so iron 2 forms insoluble basic hydroxides. Zinc 2 is an amphoteric hydroxide which will be able to dissolve in excess sodium hydroxide as well as aqueous ammonia. Okay, so it depends on which one you want to use. Okay, yeah. And do read the question carefully when they ask you to separate them. Do they want it in the aqua form, or do they want it in the complex form, or in the hydroxide form? Okay, so for the test, to 1 cm depth or to 1 cubic centimeters of Fa1, for example, add excess sodium hydroxide. Yeah, so I will be able to precipitate out iron 2 hydroxides. Okay, and for the filtrates, it's actually a colorless filtrate because it contains the zincate complex. Okay, then how am I going to isolate the zincate complex and zinc hydroxide? Do I add hydrochloric acid dropwise until I get some precipitate? So my suggestion is you probably don't want to do that. You can just neutralize the whole solution and then add sodium hydroxide until the precipitation or until you get maximum precipitate. Yeah, you can actually view it. I mean, if you observe carefully, you will notice that when more and more hydroxide is being added, right, the solution starts to clear up. So I think you have to be a little bit careful about this. Yeah, but again, the question didn't say whether you're supposed to separate them as the hydroxide or what. So in this case, it is perfectly fine separating zinc 2 as a zincate. Okay, you do need to be very careful about the green PBT, because it will be very readily oxidized to iron 3 hydroxide in the presence of air. Okay, because it will undergo aerial oxidation. Okay, as what most of you observe in your laboratory work. Alright, so we have come to the end of the H2 chemistry series. I hope you enjoy this series of lectures, and for future videos we'll largely touch on revision materials as well as laboratory skills. I thank you for listening for the past 1.5 years, and look forward to creating more videos for your learning. Thank you very much.